Hello everyone. In today's presentation, I will be talking about cooperating processes and inter-process communication, also known as IPC. First of all, let's see the two types of processes that exist in operating system. The first type is called independent processes. These are the processes that run completely on their own. They don't affect any other process and they are also not affected by any other process. You can think of them like two people working in separate rooms and having no communication at all. The second type is cooperating processes. These processes can affect each other and they need to share data or work together to complete a task. And that's exactly where IPC comes in. IPC is the mechanism that allows these cooperating processes to communicate with each other and synchronize their actions. So now we have seen the types of processes and what is basically IPC. Now the question is, why do we even need IPC? Like, what's the even need of using IPC? So there are several reasons. The first is information sharing. Multiple processes might need to access the same data. For example, a file stored on the disk may be required by many people. Second is computation speed up. If we break a big task into smaller subtasks and run them on different processes at the same time, then the overall task finishes faster. Then the third comes resource sharing. Processors share hardware and memory instead of one needing its own separate copy. So it reduces the requirement of memory space. Then we have modularity, which means it's easier to organize a complex task by splitting it into smaller process or threads, each handling one task. Like basically, if you will completely do a whole task at once, it will be very complex. So it would be much easier if you break it into smaller subtasks. And then lastly comes convenience. A single user can run multiple programs at the same time to perform different tasks, like having a browser, a music player, and a code editor to all open together. Now comes various types or ways of IPC. So, let's start with shared memory. In this method, multiple processors are allowed to share a common region of virtual memory. So basically, both processes can read and write to that same memory area. And the biggest advantage of shared memory is that it is easiest to manage because both processes might try to access that memory at the same time, which can cause conflicts. So synchronization is also the thing which becomes important here. And as you can see in this diagram, multiple processes can read and write to the shared memory region. Now comes the producer consumer problem. It is a very classic example to understand shared memory. So, here we have two processes, a producer and a consumer. The producer creates or produces some item and the consumer consumes that item. Now, both these processes share a common space in the memory called a buffer. The producer stores the item it creates into this buffer and then the consumer picks up the item from the same buffer whenever it needs it. Now comes the buffer problems. So there are two versions of producer consumer problem. The first is called the unbounded buffer problem, where the producer can keep producing items continuously and there is no limit on the size of the buffer. It just keeps growing. And the second one comes bounded buffer problem, which is more realistic because here the buffer has a fixed size. So a producer can only produce up to that limit, and once the buffer is full, it has to wait until the consumer consumes some items and like free up space. Now here comes the code of producer consumer problem. So let's look at the actual pseudocode for bounded buffer problem. On the left, we have the producer code. It keeps producing an item and checks if the count is equal to the buffer size. If it is full, it does nothing and waits. Otherwise, it places the item into the buffer, updates the index and increases the count. As you can see, count is increased by 1. On the right side is the consumer code. It checks if the count is 0, meaning the buffer is empty, and so it waits. Then otherwise it picks up an item from the buffer and decreases the count. Now, here comes an interesting question. What can go wrong if both these processes run at the exact same time? So think about it for once. So basically, let me tell you, this is where synchronization issues like race conditions can occur, where the key challenge in shared memory system, the key challenge occurs in the shared memory systems. Now comes the second type, which is message passing systems. Message passing systems, unlike shared memory, in the message passing, there is no shared variable at all. The IPC facility here provides two basic operations: send message and receive message. So, if two processes, let's say P and Q, want to communicate, they first need to establish a communication link between them, and then they exchange data using these send and receive operations. Now, let's just see this message passing diagram. This diagram shows exactly how message passing works between two different processors. Here the processor 1 is the sending process. It has some data in its memory. That data is packaged into a message which includes source process and the destination process information and sent over the network to processor 2, which is the receiving process. The data then gets stored in the receiving process memory. Now comes the key issues. So there are basically two key issues that need to be resolved in any message passing system. First is direct or indirect communication. This is also called naming. And the second is whether the communication is synchronous or asynchronous. Now let's understand both of this in detail. First comes direct communication. Starting with direct communication, here the sender must know the exact name of the receiver to which it wants to send a message. And there is one-to-one link between every sender and receiver there. Like there is one-to-one link between a sender and a receiver. So within direct communication, there are two types. Symmetric communication, where the receiver also needs to know the specific name of the sender it wants to receive the message from, and asymmetric communication, where this is not necessary. It means that the receiver does not need to know exactly who is sending the message. So now comes indirect communication. Here, instead of direct sender receiver links, processes use shared mailboxes, or what we also call ports. Multiple processes can share the same mailbox. But here's the catch. Only one process can actually read any given message from that mailbox. Initially, whichever process creates only one allowed to read mail from it, although this ownership can be transferred later. So the operating system must provide system calls to create, delete, send, and receive messages from these mailboxes. Now let's just move ahead and see what is synchronous and asynchronous communication. In synchronous messaging, the client sends a message and then waits for the server to respond back. Basically, a message flow in both direction, to and from. And in asynchronous messaging, the client does not wait for a response. It just sends the message and moves on. An event is used to trigger a response from the server later. So basically, even if the client goes down in the meantime, the message will still complete successfully. So this is basically one-way communication. The flow only goes in one direction. So this was all about synchronous and asynchronous communication. And hence we come to the end of this topic. So that wraps up our discussion on cooperating processes and inter-process communication. We covered what IPC is, why we use it, the two major types, which are shared memory and message passing, along with real life examples like producer consumer problem, and the key issues in message passing like direct indirect communication and synchronous asynchronous communication. So yeah, that's all. Thank you so much for watching, and I hope this explanation was clear and helpful. Thank you.